Okay. Hi, everyone, again. So we continue with second lecture by Clay.
Welcome back. Okay, so this lecture will be about symmetry and its generalizations. So in the first talk, we saw that symmetry and anomalies are very important, in particular because they are a normalization group invariant. And so what we like to do is latch onto that idea and develop as many kinds of concepts of symmetry as we can so that we can develop all sorts of renormalization group invariants. Okay, so we're going to discuss topological operators. And this will be a viewpoint on symmetry that does not use conserved currents. That will be its main virtue. So to start, what is our initial definition of a symmetry? So initially, we think that we have some charge, we'll call it Q, and we define Q by the integral over space of J0. So this is our starting point, and we'll eventually abstract from this away, but here we use the current to define a charge. So this is a conserved charge. And it's conserved precisely because J is conserved as an operator. So this is a very Lorentzian kind of formula. We've singled out time as being special, and we're integrating over space. If we want to do QFT in Euclidean signature, what are we supposed to do? So more generally, we can think of, so for Euclidean QFT, we can define a charge which we think of as Q, and it will depend on some d-1 manifold. So here we'll be in, we'll have a d-dimensional QFT, and this will be defined by the integral over that md-1 manifold of star J. So J is a 1 form, so the Hodge star of it is a d-1 form. So this integral looks good as an integral of differential forms. And I remind you that d mu J mu equals 0 is the same as saying that d of star J as a d-1 form is 0. So this is a kind of generalization of this formula, because here md-1, we imagine it could be any d-1 manifold. So here we're just talking about some spatial slice, maybe rd-1. Here md-1 could be a sphere, for instance. So we can also consider exponentiated versions of these. So these were the charges. We could look at the associated group elements. So we could define U alpha of md-1, which we say as the exponential of the charge. So this label alpha here now becomes a group label. So here I've written some notation that suggests that the symmetry group is U1, and alpha is some phase telling us how far in U1 we've gone. So far I didn't use much. I didn't do much because I started with the J's, and I just defined charges and group operators. But these operators will be preferred in our discussion Preferred over what? They'll preferred over the discussion of the current, using the current, because they don't require the current. So they're preferred because a discrete symmetry, say like a Zn symmetry, has no current and no charges, but will have the U's. So we'll unpack that in a little bit, but I'd just like you to see where we're going and why it is that we've introduced these operators. So these operators U are sometimes also called, they're sometimes called symmetry defects. And now let's talk about what are their key properties. So they have several. So U alpha of MD minus 1, you could ask, so here this operator depends on the manifold MD minus 1. In this formulation we define it as an integral over a manifold. But you could ask, how much does it depend on this manifold? And the answer is that it depends only topologically. On MD minus 1. What does that sentence mean? It means that if I make a small deformation of MD minus 1, the operator stays the same. Let's exhibit that. Let's exhibit it using the form that is related to currents. So, for instance, if I integrate star j over a D minus 1 manifold, and I compute the difference of that of the same integrand, but now over a slightly deformed manifold. So this is a slight deformation. So this equals, by Stokes' theorem, so I think of the difference md minus 1 and m tilde d minus 1 as being the boundary of some larger manifold xd, some d manifold, and then I'm supposed to integrate the derivative. And this is 0 by current conservation. So these operators are special because they are topological. So they're not just any operator on some D minus 1 manifold. They depend only topologically on that manifold. And that's equivalent to the notion of the current being conserved. Okay. So what's the next key property? Next key property is that U alpha, this topological operator, implements symmetry transformations on operators. Okay, so let's draw a picture associated to that. So let's let here be a local operator O. It's at some point. I'll call that point 0. Now I will surround this local operator with a symmetry defect. So this will be U alpha on some D minus 1 sphere. Now this symmetry operator is topological, and if it weren't for this operator, this sphere is null homologous, right? We're just talking about a sphere embedded in kind of a trivial ambient space right now. And so if it weren't for this local operator, I could just shrink this sphere to nothing, and the operator would be trivial by the first key property. So what I can do instead is after I move the operator past, outside of the sphere, then I can shrink the sphere to 0. So what we get by this logic is some kind of rule for what happens when we move the operator past. So we get the same operator times a phase, e to the alpha qo, where this is the charge of O. Where does this kind of formula come from in the usual language of conserved currents? It comes from the fact that d of star j is actually not quite 0 if you have a local operator. But there's the Ward identity correction, which says that this is like the charge of O times a delta function at the location of O. So I can, when I do this kind of formula, so I try to move this sphere off of this operator, and I use that formula over there, and then I find that d star j is not 0, it has this Ward identity correction, and I pick up this additional contribution. So this is what I mean when I say that the symmetry defects, these U alphas, implement the symmetry transformations on operators. So here in our discussion, as I was saying before, we use the currents, but we could kind of invert the logic here, and that's a good idea. So we could say that U alpha being topological is actually equivalent to current conservation. So now I'll just forget about U alpha being, I'll forget about the current conservation, and I'll just remember that U alpha is a topological operator. That already has that information in it. And similarly, this kind of rule for how U passes through local operators is equivalent to the Ward identity. So now I just forget the Ward identity. So with this kind of logic, in general, in quantum field theory, we can define the global symmetry by the existence of topological operators. These symmetry defects, obeying items 1 and 2. So where is the data of the group? So here I said symmetry group, and so far I didn't mention a group. So that's in the fusion algebra of the symmetry defect. So we could take U sub G1 along some manifold, and U related to some other transformation, G2. And when we multiply them, we get U of G1, G2 on the same locus. So this multiplication encodes the group law. So this is going to be a viewpoint on symmetry that does not require conserved currents. So it will enable you to make sense of things like discrete symmetries. Let's try to make it a little more concrete by thinking what the symmetry defects are in some kind of simple example. Let's take an example which is an Ising model. The Ising model has Z2 symmetry. Because it's discrete, there's no Noether current. There's no notion of an infinitesimal transformation, but there will exist these defects. How would we define them? So let's imagine it's a 3D Ising model, so we could draw pictures. So here's where we want the Z2 symmetry defect to be. How does it act on the degrees of freedom? How do we think about it? So it's an Ising model, meaning that I'm thinking about it as being characterized by some spins which can either be up or down. So over here, say there's some configuration of up, then what the defect does is it just flips the spins everywhere to the left. So the point here is that a defect being codimension 1, symmetry defect codimension 1, cuts space-time into two pieces, a left half and a right half. And the action of the symmetry defect is to flip all the field variables by the Z2 transformation everywhere in one half of your space-time. Now that actually sounds a little funny because it sounds like I'm saying that the defect acts on, it sounds like I'm saying it acts on a manifold of dimension d. But really it's supposed to be associated to this submanifold of dimension d minus 1. And the point is that since this is a symmetry, if you flip all spins over here, it actually doesn't cost you any energy. There's no noticeable effect of this because this is a symmetry. So all the kind of interesting behavior, the interesting energy and momentum of this object is happening right at the interface. So we only detect the insertion at the defect. And what I'd like to say is that just as in our, to stress the importance of these U's, so you might again think that this is overkill because can't I just work with the current? And the point is that in this kind of example, this symmetry defect is not the integral of anything local. So there's really no alternate point of view on what this symmetry is, other than the existence of this symmetry defect. Questions?
So if you have something like U1 and you have these topological operators, can you establish the existence of a local current?
That's a good question. So you want me to literally invert the dictionary. Yeah, so up to some pesky like axiomatic field theory issues, I think you can. What you want to do is look at a very small manifold and try and take the log of the operator. And then you want to show that that log is a local operator. And that's where some pesky issues will come in, kind of establishing that that is really a local operator. But I think morally speaking, the answer is yes. Any more questions? Okay, so that was all about what we might call ordinary symmetries. So Zn symmetry, U1 symmetry, whatever you might think. But it gives us a suggestive path to generalize the notion of symmetry. So I'd now like to introduce higher form global symmetry. So what's the definition? So we'll say that a Q form global symmetry is characterized by topological operators of codimension Q plus 1. So we'll denote them by U, G, and they can be put on manifolds of dimension d minus q minus 1. So that's the definition. So the case we were just studying in this notation is zero form symmetry. That's the standard global symmetry. Q form, where q is greater than 1, will be something new, and we'll discuss what that is. But first, let's just track through what's going on with the charges of these operators. So first comment is that the charged operators are extended operators with dimension q. So that's what Q labels. It labels what is the dimension of a charged object. So for a zero form symmetry, the charged object is a point-like local operator. More generally, we'll have extended operators. But the picture of them being charged is the same as the one that I erased before. So let's imagine here's some operator L, which is dimension Q. And we can surround this with some UG, that's being some S d minus 1 minus Q, linking L. And just as before, we can remove this symmetry defect if we pay the price of inserting the charge. Well, let's call it alpha. So that's the notion of something being charged. What about the Hilbert space notion of something being charged? So when I initially introduced a charge, I imagined that it was defined as something acting on a spatial slice. These operators don't have the right dimension to fill up a whole spatial slice, because Q is, in the interesting case, Q is bigger than 0, and so this is a smaller dimension manifold than a whole spatial slice. What that means is that in the Hilbert space picture, so let's say space is some manifold which is a d minus 1 manifold, y d minus 1. We'll have that a Q-form symmetry gives one charge for each d minus 1 minus q cycle in y d minus 1. So just as a gut check, when q was 0, the only non-trivial cycle was the thing that filled the whole space. That was the standard notion of charge. But if q is larger than 1 and y is a more interesting manifold, then we'll have many charges in general that we get from a single Q-form symmetry. Okay, there are kind of too many letters floating around on the board here. In particular, it's sort of annoying to keep track of Q in general, and it's actually, it turns out to be not that interesting to keep track of, to do the theory of general Q. The case that is really most interesting seems to be Q equals 1. And the reason that is the most interesting is because it seems fundamental in gauge theory. So I'd now like to tell you about one-form global symmetry in gauge theory. So, first of all, what is a continuous one-form symmetry? I emphasize the U's as being a better general point of view because they exist for discrete symmetry, but let's warm up by again returning to the continuous symmetry case. So a continuous one-form symmetry is related to a conserved current with two antisymmetric indices. So remember that d mu of j mu nu being 0 is the same as saying that d of star j, which will now be a d minus 2 form, is 0. So that would be the right dimension to form charge operators of codimension 2. Okay, how do we get examples of this? So 4D Maxwell theory gives you some nice elementary examples to work on of this phenomenon. Any questions? Okay. So 4D Maxwell theory has two such operators. So it has, first of all, d mu of f mu nu equals 0 by the equations of motion. By Maxwell theory, I mean no charged matter, just free abelian gauge theory. And this leads us to a one-form symmetry U1. Here, this superscript is to remind us that it's a one-form symmetry. And since this is related, as we'll ultimately see, to electric charges, we call this the electric one-form symmetry. Now, it's also true in Maxwell theory that the divergence of star f mu nu is 0. And this is by the Bianchi identity. Or this is the Bianchi identity. And so we have another conserved current with two indices. So we have another U1, one-form symmetry, and we call this one the magnetic one. Okay, let's investigate this picture in this context. So the charged objects are lines. So let's say a line L is at the origin of space and extended in time. So then we could take the integral of 1 over 2 pi. We're supposed to put star of the current. So this was the current. So we put, for the electric one, we put star f. That's what we were supposed to integrate over some S2 surrounding this origin. And this is, of course, the electric charge. So that's why this one is called, the one-form symmetry is called the electric one-form symmetry, is because it measures the charge of Wilson lines, the electric charge. Okay, we do the exact same calculation for the magnetic one. Now we put the star and we get just F, and this is the magnetic charge. That's why this one is called the U1 magnetic symmetry. So the charged objects under this one are, say, 't Hooft lines. No questions, okay? So this is defining the symmetry by the current and its action on charged objects, namely line operators. You might have asked for something even more primitive, which is that usually if we have a continuous global symmetry, we can just say that there's some transformation on the field variables, which leaves the action invariant. Can we do that here? And the answer is yes. So let's do that. So let's examine U alpha for the electric one-form symmetry. I guess I should put a 2 pi if I'm really being consistent. So it's defined on sigma. What would sigma be? Sigma is some 2 manifold. So we'll work locally. That means I'll take sigma to be R2, which is the xy plane at t equals z equals 0. And I'll set temporal gauge. For convenience, so that means that AT is 0. That implies that star f sub xy, that's the components I need to know to do the integral, is just equal to dt of az. Now, dt of az is canonically conjugate to az. So that means that I can easily now evaluate u alpha of sigma ai, u alpha of sigma inverse. So I can figure out how u alpha acts on the field variables. So it just gives back ai for I is x or y. Finally, if I is z, we get some shift, because since this is canonically conjugate to az and we're exponentiating it, we get just the shift operator. So we get, for the other case, az plus alpha delta of z delta of t. So here I'm imagining that this is a function of z and t. So we shift the connection, A, by this bit here. That's the field transformation. This was for the electric symmetry. For the magnetic one, things are not so simple. It's not so easy to write a formula that just transforms the fields, precisely because when you would do this, you wouldn't find time derivatives. So if you want to write a similar kind of formula for the magnetic symmetry, you need to work in dual magnetic variables. Now, there's a third definition. Which is a disorder definition. So U alpha, let's again think about the electric U alpha. It's a codimension 2 object. So if I look at the normal space, it looks like a point in a plane. So we're in 4 dimensions, and U alpha extends along 2 of them. So I'll think of it as a point in some ambient plane. So here's U alpha. And around U alpha is therefore a distinguished 1 cycle. Let's call it small gamma. So gamma is the 1 cycle that's very tiny in just a little neighborhood of U alpha. So what I'm going to do is I'm going to define the correlation functions of U alpha in a disorder way, meaning I'm going to integrate only over connections obeying some condition that is defined by this geometry. So we define insertion of U alpha by integrating only over A's with the integral along gamma of A equal to alpha. So this is another way to define what you mean by inserting this operator into the path integral and to compute correlation functions. You integrate only over A's with that behavior. Okay. This was all for the free, non-interacting Maxwell theory. What happens if we introduce charged matter? Okay, so let's imagine here, I'm going to focus, I've been focusing on the electric symmetry, I'll continue to do so. So let's insert here a Wilson line. Let's say the charge of the Wilson line is n. So that was something that was charged under the one-form symmetry before, the electric one-form symmetry. But now if I have dynamical charged matter, we're all familiar with this effect where the charge pops out of the vacuum in pairs, and the pairs rearrange themselves to try and cancel the bare charge of this electric Wilson line. So nucleated pairs try to screen the Wilson line charge. That's what's responsible, for instance, in the running of the gauge coupling in electromagnetism, has this kind of picture. So that screening means that if I try to measure the electric charge by surrounding this line with a two-sphere, the measured electric charge would depend on distance scale. It would depend on whether the sphere was very big, in which case I might not see any charge because of these nucleated pairs, or very small, in which case I would detect the bare charge. So that means that the U alphas are no longer topological. So the effective charge of L now depends on distance. So this implies U alpha, the electric one, not topological. So we would say that the symmetry is broken. So charged matter can break this one-form symmetry. How badly does it break it? So let's imagine more generally the particles say they have charge k. And let's imagine that k is greater than 1. In this case, we'll see that you cannot, well, it's sort of clear from the picture, you cannot screen an arbitrary Wilson line. You can only screen charges that are multiples of k. So what that means is that you have, in this case, U1 one-form symmetry, the electric one-form symmetry, is broken by the introduction of these charges down to ZK, one-form symmetry, where k is the charge of the particles. How do we see it more technically? So let's look at integral. This was the thing defining the one-form symmetry before introducing the charged particles. And we'd like to test whether it remains topological. So let's imagine wiggling sigma 2 a little bit. Well, I'll just call it sigma. Sorry, let's do it this way. This minus that equals, again, the integral over some x, which is a 3-manifold, the difference between them, of I alpha okay. Sorry? There should be a minus here. Yes? This minus this. Yeah. This is a product of two things. This times this, but there's a minus sign. So that's like asking what's the difference, how does this operator change if I wiggle sigma a little bit? Okay, now this is, by the equations of motion, this is just the electric current for the dynamical matter. Right? D star F is J electric. And now if we're imagining that the charged particles have charge K, it means that when we integrate J electric over some 3-cycle, we're going to get something that's a multiple of K. So this is 1, which is what we need, if alpha is restricted to be 2 pi L over K, where L is some integer, and K is the quanta of charge. So this is J electric, and what I'm using here is that integral of J electric over x3 is some multiple of K, because I've assumed that the charges, well, I shouldn't use that N. I've assumed that the charges are quantized in units of K. So this is how you see technically that if you have not minimally charged particles, that you still have some one-form symmetry left over. And what it means is that you can still define a conserved quantum number that measures the charge of the Wilson line modulo K. That will still be conserved in all correlation functions. Oops, I don't want to erase this. Well, it's kind of too late. What about the magnetic one-form symmetry? Charged matter, that is electrically charged matter, doesn't affect that at all. In order to break that, you'd have to introduce dynamical variables that are magnetically charged. So if you have dynamical monopoles, that will break the magnetic symmetry. So for instance, if you have a U1 gauge theory that comes from, say, SU2 by Higgsing, then there are dynamical monopoles which have some scale set by the Higgsing scale, have some mass set by the Higgsing scale. And at the scale of where those look dynamical, the magnetic symmetry would be broken. So that's an example of how to break that symmetry. Okay, that was all about one-form symmetry in abelian gauge theory. But where we'd really like to get to is to non-abelian gauge fields. So let's again come back to our old friend, SUN Yang-Mills. And for the purposes of this discussion, the global form of the gauge group will matter. So what I mean is that the following discussion would depend on, say, SU2 versus SO3 gauge theory. Now, you might not even be sure what do we mean, what is even the difference between SU2 and SO3 gauge theory. And part of what the following discussion will be about is what is really the difference between those two gauge theories. Okay, so first of all, let's be in SUN, where I mean that is the global form of the gauge group. And let's discuss Wilson line operators. We've seen that one-form symmetry is all about line operators, and so the natural line operators to study here are Wilson lines. And we know that Wilson lines are associated to representations of the gauge group. So this is the first place where you see the global form entering. If you were discussing Wilson lines, if you had SO3 gauge theory, your Wilson lines would have to be honest representations of SO3. So the vector would be an allowed Wilson line, but the doublet would not be. Whereas if you were talking about SU2 gauge theory, the doublet is an allowed Wilson line. So the spectrum of line operators can detect some details about the global form of the gauge group. So it will be important, we don't need to know too much about representation theory, but one thing we do need to know is that all the representations can be made from the fundamental. So the fundamental would be denoted by n, or in a Young tableau notation by a box. And when I say all representations can be made from this, I mean that if you start with this basic n-dimensional representation that defines SUN as a group, and you start taking tensor products and symmetrizing them, you'll eventually get every representation that exists of SUN. So for instance, we can have the symmetric square of n, and we would denote it in this way by two boxes, or wedge squared of n, the antisymmetric part, and you denote it by this. We often are interested in the adjoint. That looks like this kind of hook Young diagram. Okay, and it goes on forever. They're characterized by Young tableaus in some shape. It's also useful to note that the center of SUN is of the form lambda times the identity matrix, where lambda is an nth root of unity. Okay, so this is just a comment about representations. What's it good for? Well, we can define a useful quantum number. So definition, the n-ality of a rep, or of a representation, is defined to be equal to the number of boxes in it mod n. So for instance, we'd say that the fundamental has n-ality 1, the symmetric square or antisymmetric square has n-ality 2, etc. It's only defined mod n. So this is some number in Zn. And because of this comment about the center, this is equal to the charge of the representation under the center. So the center of SUN is the group Zn. And so every representation can be characterized by how it transforms under the center. And since it's Zn, it has possible charges 0 up to n minus 1, all thought of mod n. Okay, so now comes a crucial moment. So far I've just been telling you about representations of groups. So let's go back to our discussion of screening. So in pure Yang-Mills, which is what we're discussing right now, there is only adjoint matter. Right? So the only fields in the problem are gluons, and the gluons carry adjoint indices of the gauge group. So what is the n-ality of the adjoint? Well, the adjoint representation has exactly n boxes, and so the n-ality of the adjoint representation is 0. So this means that we can only screen lines of n-ality 0. So therefore, there is a conserved quantum number associated to lines in SUN Yang-Mills. So based on our previous discussion, we will conclude that SUN Yang-Mills has one-form symmetry. The one-form symmetry is Zn. So just to hammer it home, how does this one-form symmetry work? So if you have some Wilson line L, and here's U alpha surrounding it, and alpha has to be an nth root of unity. So this is exp I alpha n-ality of L, and then again L. Since alpha is an nth root of unity, this is okay that it's okay here that the n-ality is only defined mod n. So this is the definition of how it acts on the operators. And you can see, based on this physical argument, the fact that we can't screen, that's why there's really a symmetry. You can also chase down and write the transformation on fields, or you could define these operators by a disorder definition, just like we did for the abelian gauge fields. But I won't do that right now. Questions? Okay, so why do we care about this symmetry? It seems pretty fancy. Well, one good physical reason to care is the following. There is a connection of this symmetry to confinement. And in the last few minutes, I'll explain to you how that connection works. So the basic point is that one-form symmetry helps us to understand with gauge theory phases. So what will be the punchline? The punchline is that we have this one-form symmetry, Zn1, and if it is spontaneously broken, this will turn out to be synonymous with saying that the theory is deconfined. If it is preserved at long distances, then this will be synonymous with saying the theory is confined. So this is really the meat of this formalism. For ordinary global symmetries, we're familiar with kind of the Landau paradigm of various phases where you either do or don't spontaneously break a global symmetry. And there, prior to the introduction of this one-form symmetry, there wasn't really such a natural, clean notion of how to think about phases of gauge theories in that language. But here we see that with this notion of symmetry, we can think of confined or deconfined as just kind of a standard Landau paradigm. There's some symmetry that either is or is not spontaneously broken. Okay, so let's sketch how this connection works. So this is usually phrased in terms of perimeter versus area law. That is, confinement or deconfinement is usually phrased in that way. So what do? So we draw a Wilson loop, and we think of this Wilson loop as having some spatial separation r, and then some long time that it goes this way, t. And we take the expectation value of this, and it goes like e to the minus perimeter for a deconfined phase, or e to the minus area for a confined phase. So for large R, and t going to infinity, so imagine R is very large and t is even larger and being taken to infinity, we can actually view this configuration that we're trying to study as a sum of lines. So the sum that I'm talking about, one of them is the one that goes here. You should think of it as running infinite in extent. And the other is the one that goes here, also runs infinite in extent, because I'm taking t to infinity. So if it is confined, then the infinite Wilson line infinite length Wilson line, which I'll draw like this, has expectation value 0, because this decays like t. What about when it's deconfined? Well, we want to do the same thing where we pull apart the line. And here you have this perimeter factor. So the perimeter factor in the law for Wilson lines, in the perimeter law, you can actually think of that as just saying that you dressed your Wilson line with some counter term. Right? You can always absorb the perimeter by putting a local term on the line, a term proportional to the length. So it's actually convenient to do that. So then when you do that, we'll have that in this case, this is non-zero. So this is, here I've added perimeter counter term. Okay, so the basic point in this discussion is that the two different phases can be distinguished by saying that some object either does or does not have an expectation value. Okay, so let's conclude now by connecting it to symmetry, namely one-form symmetry. So I claim that this infinite length Wilson line is charged under U of sigma, where alpha is the generator of Zn, which sigma? Well, it's the sigma intersects, it's the sigma that intersects the line if they were at equal time. So you can think here that sigma is like R2 for the purposes of this discussion. So maybe it's helpful to draw a picture. So we define the charge in terms of linking. It'll be a little bit hard for me to draw a picture with the accurate dimensionality, so I'll go down one dimension. So let's imagine here's L. It's extended in space. This is L, this line. And what we know is that if we loop the one-form symmetry around L, it's charged, right? Because the one-form symmetry measures the charge. So now let's ask ourselves, what happens if we consider, let's see, it's really impossible to draw. Oh, actually, let's draw it even smaller codimension. So L will now be a point. Okay. Now, let's take, here's sigma. And here's, so this is sigma at t equals plus epsilon, and here's sigma at t equals minus epsilon. And we're considering u sigma. So if I try to move this u sigma through here, the difference between them is the sphere surrounding L, which measures the charge. That's how I get this conclusion. So difference between these two, let's call this sigma tilde. So u sigma times u sigma tilde inverse is e to the I q, let's give them alphas, ql times L. So what we learn is that this infinite line is charged under the one-form symmetry. On the other hand, we see that the phases of the gauge theory that we're interested in can be distinguished by whether this operator has an expectation value or not. So that is the standard symmetry breaking paradigm. It means that the phases are being distinguished by whether a charged operator has an expectation value or not. The case where it has an expectation value is this one. That's deconfined. And so we see, as claimed, that in this case, Zn1 is spontaneously broken. Here, the charged operator, this infinite Wilson line, has no expectation value. So here we see that Zn1 is preserved. This is the main reason for caring about the one-form symmetry. Okay, so I'll stop here.
Any questions? Okay, I suggest we take a 5-minute break and then we reconvene for the discussion. So please prepare your questions. I think if you want to discuss something or if you're completely lost, you just can. It's time to say. It's time to know to try to get back on track. So let's get back in 5 minutes and let's thank Clay again. Thanks.